Imagine a world without light, without the warmth of the sun, without the convenience of your smartphone. This is a world without electromagnetism. Electromagnetism is the invisible force that shapes our universe, from the smallest atoms to the largest galaxies. It binds electrons to atoms, allowing for the formation of molecules and all matter. It governs the behavior of light and the interactions between electrically charged particles. Understanding electromagnetism is key to unraveling the mysteries of the universe. In this journey, we will delve into the fascinating world of electromagnetism, exploring its fundamental principles and its profound impact on our lives. In the annals of science, few names shine as brightly as James Clerk Maxwell. Born in Edinburgh, Scotland in 1831, Maxwell was a child prodigy with an unquenchable thirst for knowledge. He excelled in mathematics and physics, making significant contributions to both fields. Maxwell's greatest achievement was the unification of electricity and magnetism into a single, elegant theory. Through a set of 4 equations, he showed that electricity and magnetism are 2 sides of the same coin. His insights revolutionized our understanding of the universe, paving the way for countless technologies. From radio waves to gamma rays, all forms of electromagnetic radiation owe their existence to Maxwell's work. Maxwell's legacy extends far beyond his scientific contributions, inspiring generations of physicists. Imagine a single point charge, a tiny speck of electricity sitting alone in space. This charge creates an electric field, an invisible aura that extends outward in all directions. Gauss's law, the first of Maxwell's equations, quantifies this relationship between electric charges and the electric fields they produce. Think of a balloon, inflate it, and the air inside pushes outward on the balloon surface. Similarly, an electric charge creates an electric field that pushes outward. Gauss's law tells us that the strength of this push, the flux of the electric field, is directly proportional to the amount of charge enclosed. Picture a sphere surrounding our lone charge. Gauss's law states that the total electric flux through this sphere is directly proportional to the charge enclosed within it. This fundamental principle underpins our understanding of electrostatics and forms the bedrock for many technological applications. From designing capacitors for electronic circuits to understanding lightning discharges in the atmosphere, Gauss's law is essential. Unlike electric charges that exist in isolation, magnets always come with 2 poles, a north pole and a south pole. Try as you might, you can never isolate a single magnetic pole, a so-called magnetic monopole. This fundamental difference between electricity and magnetism is captured by Gauss's law for magnetism, the second of Maxwell's equations. Imagine a magnet, its north and south poles clearly marked. Now surround this magnet with an imaginary closed surface. Gauss's law for magnetism tells us that the total magnetic flux through this surface is always 0. This means that the number of magnetic field lines entering the surface must equal the number of lines exiting it. This duality is a key feature of electromagnetism, shaping the behavior of magnetic fields and influencing a wide range of phenomena. Section 5. Faraday's Law, the dance of electricity and magnetism. Imagine a wire loop, a simple circle of conducting material. Now move a magnet towards this loop. As the magnet approaches, an electric current begins to flow in the wire, even though there's no battery or power source connected to it. This phenomenon, known as electromagnetic induction, is described by Faraday's law, the third of Maxwell's equations. Faraday's law tells us that a changing magnetic field creates an electric field. This induced electric field can drive an electric current in a conductor. Faraday's law is the foundation of countless technologies, from electric generators to transformers and electric motors. Section 6. Ampere-Maxwell equation, completing the puzzle. While Faraday's law told us that a changing magnetic field can produce an electric field, Maxwell realized something crucial was missing. Could a changing electric field in turn produce a magnetic field, completing the symmetry? Maxwell's addition to Ampere's law, the fourth and final equation, provides the answer. Ampere's law originally stated that an electric current flowing through a wire creates a magnetic field around it. Maxwell's insight was to realize that a changing electric field could also act as a source of magnetic fields. Imagine a capacitor, 2 conductive plates separated by an insulator. As the capacitor charges, an electric field builds up between the plates. Maxwell realized that this changing electric field would create a magnetic field, completing Maxwell's equations and revealing the beautiful symmetry between electricity and magnetism. Section 7. Electromagnetic waves, riding on Maxwell's equations. Maxwell's equations, once assembled, revealed a breathtaking prediction: the existence of electromagnetic waves. These waves could travel through the vacuum of space at the speed of light. Imagine a ripple in a pond spreading outward from a dropped pebble. Similarly, an accelerating electric charge creates a disturbance in the electromagnetic field, a ripple that propagates outward as an electromagnetic wave. This wave consists of oscillating electric and magnetic fields, perpendicular to each other and to the direction of wave propagation. Maxwell's calculations showed that this speed matched the experimentally measured speed of light, unifying light and electromagnetism. From radio waves to gamma rays, the entire electromagnetic spectrum is a testament to the predictive power of Maxwell's equations. Section 8. From Hertz to Hertz, confirming the existence of electromagnetic waves. While Maxwell's equations predicted the existence of electromagnetic waves, it was up to experimental physicists to confirm their existence. Enter Heinrich Hertz, a German physicist who in 1887 devised a brilliant experiment to generate and detect these elusive waves. Hertz used a spark gap generator, two metal spheres separated by a small gap, to create a rapidly oscillating electric current. This oscillating current, according to Maxwell's theory, should produce electromagnetic waves. To detect these waves, Hertz used a simple loop of wire with a small gap at one end. When Hertz turned on his apparatus, a tiny spark jumped across the gap in his detector, confirming the existence of electromagnetic waves. Hertz's experiments validated Maxwell's theory and opened the door to the era of wireless communication. Section 9. Applications of electromagnetism. From the mundane to the miraculous, applications of electromagnetism permeate every aspect of modern life. Our homes are lit by electricity, generated and transmitted using principles of electromagnetism. Our communication systems, from smartphones to the internet, rely on electromagnetic waves to transmit information wirelessly. Medical imaging techniques like MRI utilize strong magnetic fields and radio waves to create detailed images of internal organs. Particle accelerators employ powerful electromagnetic fields to accelerate charged particles to near the speed of light. Even the simple act of turning on a light switch relies on electromagnetism. Maxwell's legacy is not confined to Earth. Radio telescopes and spacecraft rely on electromagnetic principles for exploration. Section 10. Maxwell's legacy, a universe of waves. Maxwell's unification of electricity and magnetism was a watershed moment in the history of physics. His equations revealed the interconnectedness of seemingly disparate phenomena, demonstrating that the universe is a symphony of waves. His work laid the foundation for Einstein's theory of special relativity and quantum electrodynamics. Maxwell's legacy extends beyond physics, inspiring generations of scientists and engineers. From smartphones to medical imaging, Maxwell's influence is woven into the fabric of modern life. His story is a testament to the power of curiosity and the enduring impact of fundamental scientific breakthroughs. Maxwell's equations are a window into the hidden workings of the universe, revealing the elegant simplicity underlying the natural world. Section 11. Beyond Maxwell, the quest for a unified theory. While Maxwell's theory elegantly unified electricity and magnetism, the quest for a unified theory of physics continues. The standard model of particle physics describes the other fundamental forces of nature, the strong and weak nuclear forces. However, a complete unification of all four fundamental forces, including gravity, remains elusive. String theory proposes that the fundamental constituents of the universe are tiny, vibrating strings. These strings, vibrating at different frequencies, give rise to all the fundamental forces and particles in the universe. The search for a unified theory is driven by curiosity and the belief that a simple, elegant set of laws governs the complexity we observe. Maxwell's work serves as both inspiration and a reminder that the universe holds countless mysteries, waiting to be unraveled by curious minds and bold imaginations.